briefly what we're trying to do here in terms of theory and background, then we'll continue into the experiment. So the idea here is that we're gonna have a spring, and then we're gonna oscillate the spring on, we're gonna hang the object on the spring. Let's say this is the spring relax point. Right now, you know, the spring potential energy, things like that, right? If I hang vertically, it's gonna relax somewhere. At this point, then we're gonna bring the object and then hang the object right here. As a result of object mass is actually creating the weight downward direction, this object gonna go into the spring gonna get extend little bit, and then object gonna go into a new stable point with a little bit of extension to the spring. Okay, now this will be the new relax point. Now the object is attached. Okay, and at that time, let's say this will be our potential energy 0 point, for example. That's the new relax point. So that line going to be the potential energy 0 point. Then what we're going to do, we're going to give a compression or extension little bit to the spring and then let it move. So if we do that, the spring will gonna go downward direction when it reach, this is the starting point now, right? It will compress little bit, then we're gonna let the object goes, then the spring gonna extend this point, then at that point there are gonna be huge kinetic energy because object moving downward direction. It will continuously drag the spin downward direction into a new extended point. At that point, it's gonna get a potential energy, extra potential energy to the spring. It will come back and then go up, and then we'll do this oscillation again and again forever. If there's no energy loss during the motion, then this oscillate can go again and again forever, right? So such a motion is actually called the simple harmonic motion. So that's the idea of simple harmonic type motion. So now you know different type of motion, the linear motion, projectile motion, circular motion, things like that. And then if an object oscillate around fixed point again and again, now this is the fixed point, right? This line is the fixed point. Object go up, come back all the way to here, go up again this point, then it will completing one complete circle. And then it go up again and then doing this oscillation again and again. Now the same kind of oscillation we discussed very briefly some point earlier with the simple pendulum, if you remember. Simple pendulum is an object attached to a string, mass m attached to a string. This will be the potential energy 0 point. And then you bring the string little bit further away from the initial point right here. Then object release from there. Then when you release from there at this point, you have a kinetic energy 0 point, but the potential energy is larger than 0 because the object is h distance above the ground. Then it will go into this point and then go to the other side, then come back to this point, come back to this point again, and that motion can go again and again forever. That also simple harmonic motion. So the idea of the simple harmonic motions are technically the oscillation or the object moving around a fixed point again and again with the same maximum amplitude, which means object is started right here and then other side it's going to reach the same amount of height, and then it come back to the very bottom point here, again come back to the same initial point. So that means when this object is oscillating, then the spring is oscillating right here. It go up, compress, let's say A amount, then it go downward, negative A amount relative to this line. Okay? And then it come back to the initial point, go up again, same A amount. So that's one complete circle. Okay, started here, go downward, come back to the same point, then it completing one complete circle. Since the energy is conserved, that oscillation can go forever. Okay, any sort of same kind of motions are actually simple harmonic motion. So that's the idea. Okay, that's the difference between the motion which we talked earlier in the semester, circular motion, and the projectile motion, linear motion, all of those are different type of motion. Now we're talking about this is a type of circular motion, but we can observe the motion little bit differently, like a linear motion moving again and again around the fixed point. Okay, but we can connect this into a circular motion too, because if you look at it, what's happening, this particular motion around the fixed point, it is exactly similar to the circular motion too. Circular motion means object is moving on a circle, but if you observe the circular motion in one direction, these two are going to be exactly the same. Let's say this is the fixed point. I have an object moving on a circle, on this circle, but let's observe this object only on x line, x-axis. Let's take a look what happening to the x-axis, right? So you started right here, that means this distance, let's say about a distance, right? You started right here when t equals 0. Then when you reach a to b, you can see what really happening is a decreases into 0, right? You started that, when you started right here, you started at a distance above the initial point, point P. This is the A. Right here, this is point A. When you reach point B, this amplitude right here, A, is actually reached the 0. Then if you look at what happening into the other side, B to small c, you actually moving into the negative direction. So you're moving into now negative direction slowly. And then you reach eventually maximum amplitude, negative A, negative direction. And then you continuously moving into C to D, then you come back on x-axis, 0 amplitude. And then you go back to D to A. This is A to B, B to C, C to D. And then you come back again to the starting point right here, point A. Then you reach the exactly same starting amplitude. Now, if you look at this behavior of this graph, now this is a circular motion, right? Object moving on the circular motion, but we observing that object into one direction. Okay, we observing on 1D type of situation, so we observing only on x-axis. So we try to observe only on x direction. Then it's look like sinusoidal wave function. And if you observe right here, what is happening along x-axis, object is started right here at point A, it come back to point B, then go all the way to C other end, then come back to point B again, go to point A again. Now, if you look at it from x-axis view, then what it's doing is actually simple harmonic motion. The oscillation is around the fixed point. So it always around fixed point, go maximum amplitude, A positive side, go negative side, same amplitude, back and forth again and again. So which means circular motion, uniform circular motion is actually simple harmonic motion. Those two are not two different things. It's the same thing, depending on how you want to observe that, okay? So either way, both case can represent with this function. Now, if you take a look this graph, how the graph is behave, let's say this is time, this is the amplitude on x-axis, how far away from the x-axis from the fixed point, that's the amplitude variation. This function is a sinusoidal function. Because time equals 0, you have maximum amplitude, then it varies. Now, which means technically the simple harmonic motion amplitude function you can actually explain by using the sine function. That actually the fundamental for the chapter number 15. So we will talk about that later in the semester after next exam and then so on after the break. So that is the last chapter. Okay, we'll leave it from there, and then we will discuss more when we go into the chapter number 15. Now, what we're trying to do in this particular experiment today, we try to investigate this behavior, simple harmonic motion behavior in terms of experimental process. Okay. Now, if I want to do that, I have to have a oscillating object. So that's why we actually going to use this spring, because the spring can actually do nice oscillation like this, up and down. And then in terms of oscillation measurement, we can measure, for example, period of oscillation, right? Period of oscillation means we usually write the large T, that T represent time for one complete oscillation. time for one complete cycle, right? Object has to start from one point, go to the other end, come back to the same point. Then that's one complete oscillation. That period of oscillation connected with other variables, right? If you remember period of oscillation, if you take 1 over period of oscillation, that's called the frequency. How many oscillations per second? So 1 over second is actually, we write usually unit of hertz. So that's say how many oscillation per second, and that frequency is connected with the other parameters. For example, angular velocity omega is 2 pi divided by t. If you remember the centripetal force lab, we actually discussed that there, okay? So because omega is equal delta theta over delta t, if I consider one cycle, total angle rotated on one cycle 2 pi radian, divide by the total time for one cycle is the period of oscillation. The unit going to be radian per second. Now this omega is actually equal to 2 pi times the f. Now on the other hand, if you have a circular motion, because the simple harmonic motion is actually connected to the circular motion. Okay, this is one thing. Uniform circular motion is a simple harmonic motion itself in 1D observation. Now, if you remember, we develop an equation for the acceleration centripetal earlier some point for the uniform circular motion. End of the chapter number 4, and then we reuse on chapter number 6 again. At that point, if you remember that AC is equal minus omega square times the displacement function x. So at that point, if you remember that particular derivation, so I clearly mentioned that that is the basic equation, general equation to understand whether the motion is actually repetitive type or not. That means repetitive type means it is a simple harmonic motion. In any motion, if you want to confirm which is a simple harmonic motion, so the acceleration acting on that object which is moving up and down should be a function of displacement. And then this is a constant, that is actually the angular frequency, omega. So which means if I look at it, this particular motion, you can see now this motion goes up and down. Its acceleration should be according to this one. However, on the other hand, if you look at this object is attached to this spring right here. Since object is attached to this spring, if you look at the force acting on the object at any given moment, that force going to be the spring force. So that means force going to be acting on the spring going to be equal minus k times the x. The spring force, if you remember, that is the Hooke's law. We used that earlier when we talking about the spring potential energy. Now, if you look at it, this two angle now, object is under acceleration always, because if there's a force that should be experience the acceleration, and on the other hand, force acting on the spring going to be always the spring force from the Hooke's law. So which means these two going to be the same thing. The force acting on the spring, I can write it down from Newton's second law point of view, equal mass times the acceleration. So from here, I can simply say acceleration from these two, I can simply say acceleration acting on the object, which is simply minus k over m times the x by combining these two into together. So on the other hand, we know if it is a simple harmonic motion, acceleration should be a constant times the function of the displacement. So in this case, acceleration should be minus k over m times the x. On the other hand, if it is a simple harmonic type, it should be matched with this condition. So which means you can see clearly here by looking at these two equations, k over m should be equal to the omega squared, which means omega should be equal to the k over m square root of that. So in other words, if there is an object mass m attached to a spring with the spring constant k, mass of the object is m moving on a simple harmonic type oscillation, angular frequency of that object should be just the ratio of k over m and square root of that. And on the other hand, omega we know equal 2 pi times f, which means the frequency which is equal 1 over 2 pi times k over m. So the frequency of this oscillation should be actually depending on this equation. So by studying this, by studying this experiment, by measuring the frequency of the object, because we can measure the frequency of the object very easily by measuring the period of the oscillation, right? So this f is equal 1 over t. So by measuring the period of the oscillation, we can confirm this formula. By confirming that, we can confirm this object is actually moving on a simple harmonic motion. By confirming that, we can actually confirm all these other theories too, because we developed this on chapter number 4, very end of the chapter number 4, and then we reuse that concept on chapter number 6 on Newton laws. So we're confirming all of these concepts, Hooke's law and everything. That's the plan of this experiment. So it's a very simple experiment, but by just measuring only one variable, we're going to measure just simply the period of the oscillation. That's all, nothing else to measure in terms of physical variables. But by measuring that and then revisiting the concept we developed earlier and then combining those Hooke's law and the acceleration of the simple harmonic moving object together, we can actually confirm this relationship. By confirming that, we can confirm all the other basic theories. Okay, that's the plan. So any question? Okay, then let's continue. So in terms of now the in-class experiment, we just gonna, I leave the in-class experiment apparatus too in these last two or so experiment because you can get some idea. So what we actually needed in terms of material, we just need the spring. And if it is in-class experiment, we are using two type of spring. One is harder, one is very, very softer, okay? Which means if you apply a force, try to extend the spring, one can extend very easily, other one, it's difficult to extend, it's harder, okay? And then we need the hanger. Hanger is just like a metal rod like this, has a U-shaped thing here, and then you can put the slotted weight into that, okay? And we need the meter ruler, stopwatch, that's all really. So the whole item is actually very small like this one. This spring is hanging in like maybe around couple of centimeters long, this is smaller one. And then we have a larger and softer spring, which is very lengthier, like maybe 10, 15, 20 centimeters long, but that going to extend with the smaller force very quickly. Okay, that's a softer spring. And then that's it. Then we're going to hang it, and then we're going to attach the weight here and bring it a little bit further down, let it oscillate. It's going to go up and down. And then you're going to manually measure period of oscillation. You take the stopwatch and then going to count number of oscillation like we done for the centripetal force one. We're going to count like 5 oscillation, stop the watch, and then get the timer, and then divide that by 5. Then we can get the period for one oscillation. That is the period of motion. By knowing that, we can confirm this behavior. By confirming, we can really confirm all the other concept and theories build on that particular scenario. Okay, very, very simple experiment. It is even easier with the simulator actually. Let's continue to the simulator then. And click on this icon. This will bring you into the simulator. All right, and then you can see various options, vectors, energy, lamp, then double click on the lamp. It should bring into this page. And on that page, you can see many other different menu options. Right on your left hand side, you can see a graph which says the kinetic energy, potential energy, gravitational, potential energy, elastic, and then energy thermal, energy total. Right, so we can actually look at it how the energy varies when this object is moving, because you know this motion, different motion, we can observe different angle, right? If I observe in terms of energy concept, then you can look at it, how the energy is varies when the object is moving. If you look at it right here, has a kinetic energy, and the potential energy at that point going to be 0. And if I consider it give this extension, then it has a potential energy, but the kinetic energy going to be 0 because object becomes momentarily at rest. Then it is starting to move upward again. Right here, kinetic energy becomes momentarily 0, but it's going to get potential energy because it compresses. So I can study the whole motion. We done that particular case actually with this one, right? If you remember that question, a ballistic pendulum question particularly, we actually use that particular scenario starting right here with the potential. When it reach right here, it has kinetic energy, but the potential is actually 0. Then we can use the conservation of energy to understand how fast it move at a certain point and then so on, okay? So that particular behavior, we can see how the energies are changing each other on this graph. Not really important for this lab, but we can observe that. And then you can see in the middle the spring. You can see spring has like 2 menu options on the both side. So one side to your right hand side, it says spring constant. So its number is not given, but it says it's smaller or larger. So that means larger means you can see very thick spring, and then smaller means very thin spring. So the number we can figure out by doing the experiment, but we can arrange this accordingly. We're going to do at least 2 different type of spring, okay? So one is closer to here, one is closer to there. And to your left-hand side to the spring, you can see slotted mass, which I mentioned earlier, which we can attach into this spring. All we have to do, bring a mass, attach here. Then you can see it oscillating, energy variation, and the mass go up and down, and then you can see now it's not really moving again and again forever. It becomes at rest after some time. That's we call the damping type of oscillation. Damping means you have some sort of friction on the oscillation. As a result of friction, what will happen to this sinusoidal function is starting to damp. So damped means sinusoidal function is starting to decay slowly. So the sinusoidal function right here not going to remain in constant as the time goes on. It's going to start here with maximum amplitude, but it's going to decay slowly that amplitude. It's going to do that. That kind of process is actually called the damping. You can see the maximum amplitude slowly decaying. So decaying means there are going to be some sort of energy loss. So the energy loss is going to be there. It's not 0. Now this is not energy conserved situation. Okay? If it is not energy conserved, then my equation has to be changed. So I can't use this equation as it is to understand non-energy conserved situation. Okay? So the important thing here, first, I have to make sure energy is conserved, which means if you go into your right-hand side on the simulator, you will see damping parameter right here. The damping parameter, yeah, go ahead.
Is it happening because of gravity or what kind of friction?
No, it's not because of gravity actually.
What kind of a friction is it?
That friction itself, like if you have a spring is a material, right? If you have a material inside and out, you're dragging up and down, then that friction itself, like somebody try to drag your hand, you feel the friction to that, right? You're not going to allow to hand to extend, right? Then your hand going to be break. So that's the friction force. So you take the material and then you try to extend the material. Internal molecules is actually changing position. So the bond length going to be changed in terms of chemistry. That's the friction. It not allow it to happen easily. So there are going to be internal friction there. Okay. So always you can't have like energy conserved situation. If you have a spring, if you try to observe the energy conserved situation, you're not going to get that in general situation. And there are other friction too, like not only the internal friction. You're going to get a little bit of friction from the air because object moving up and down and the spring is very lengthier. There are going to be air friction. They are going to be starting to flow up and down around the object. So that's going to create another friction. So the energy energy conserved case is very difficult to observe in real life scenario. That's why even you have a normal pendulum, like the simple pendulum, you attach the object and then try to oscillate it. You can't get that oscillation to happen forever. Slowly it will go back to the zero. There's no any length change on the string, but still there are going to be some sort of energy loss with the air friction attached to the object, because they are going to be flow around the object. So as a result of that, energy going to be slowly losing out, and then object going to go back into zero. So that called the damping type oscillation. Now we can't really study damping type oscillation, but then we have to add another parameter for that. But if I want to study the simple harmonics, very simple pendulum oscillation, I have to get rid of the damping parameter. Okay. So that comes from various ways. This damping parameter, it can come from, for example, if the string is right here and then oscillating, it can come from this attach point too. Attach point should not create any sort of friction to oscillating in that point. That also create the damping parameter. There's various different parameter attached to that. We will take a look some of them in chapter number 15. What happens if there's a damping parameter there, then the simple pendulum whole equation has to be changed. Okay. Question. Okay, now the important thing here, make sure your damping should be at the none position. Okay? If it is at none position, if you click and drag this, let it oscillate, then that will oscillate forever. So we need actually such oscillation, not the damped oscillation. Okay. If the damping parameter here is there, then we generally call the damped harmonic oscillation type. Then we are not studying that part. Okay, make sure that is at 0. And the gravity, just leave it 9.81. We don't need to change that. We would like to study the Earth gravity, but we can select different places, but we don't need to change that. And on the top right-hand side, you will see displacement that you can click. Then you can see how the displacement is actually varies relative to the initial starting point. And then you can click the mass equilibrium point, and we can place the movable line if I want to, because I can change it wherever I want to measure. May or may not be useful. And you can click the period tracer. That will be useful, because you can see period D is actually one complete oscillation. Okay, you have to decide. You can decide at any given moment is the starting point. One period mean oscillation has to complete and then come back to the same starting point. Okay, so that period tracer will be useful. And if you want, you can click this velocity and acceleration. Then you can see how the velocity and acceleration parameters changing as a function of oscillation. So all of those will be useful. Any question? But for our experiment, none of them are important. So our experiment is just we need the time. That's all. We're not interested measuring velocity. We're not interested measuring acceleration or anything. We just interested measuring the period of oscillation, because we just trying to validate our concept and theories with the simple harmonic type oscillation or the uniform circular motion type oscillation. Okay. And then you can bring the meter ruler. So if I have the meter ruler, I can actually measure the extension. That will be useful. You can bring the timer. If I have that, I can actually measure period of oscillation, right? For example, if I click this exactly when the period tracer appear and then stop, when the period tracer becomes one complete period, I can measure period of oscillation. The problem with that, it's difficult to measure one period because the oscillation look like very faster. So I may have to measure like time for 5 oscillation, for example, and get the average of that. Okay, that's what we're trying to do. And also we can do slow-mo mode. If I go slow-mo mode, then I can measure exactly one period. Get rid of the timer, then we'll wait until it complete one tracer, that black line. Start when it is starting. Then when the tracer complete one complete cycle, then we have one period of oscillation. We can actually measure, which means this is about like 0.87 second. Okay, So very small, less than 1 second. So we can do either way. We can let it normal oscillation, let it oscillate like maybe 5 oscillation and then get the timer, or we can use slow-mo mode. Time is still corrected here, correct time it's given, so we can use that. Either way is fine, okay? Let's take a look, let's decide that in a bit, what method to use. Any question? Okay, then let's take a look our data table. So we're going to try to do a couple of investigation. For example, now you know in terms of equation point of view, this is our formula we try to investigate, right? So if you look at it that to do this investigation first, I may need to have the spring constant K. So that's very important. So which means the spring constant in your simulator is not given. It just says spring constant. So I can decide what number I wanted, whether I need the thicker spring or the lighter or the softer spring, but the constant is not given. So part 1 of the experiment is figuring out this. That can be done by doing the Hooke's law. So the Hooke's law is a very simple concept, right? If you have a spring, if you attach the object, let's say this is the relax point, the spring will go a little bit further than the relax point due to the attached force, added force right here. So accordingly, I can actually figure out how much the extension is, what's the force applied here, that's going to be mg. Then by looking at the Hooke's law, I can actually figure out the spring constant directly calculating, or I can do the graphical method. Because at this particular point, spring force is upward direction, downward force is this applied force. These two should be the same, right? Applied force is actually the spring force, but opposite. So applied force, on the other hand, K times the X. I'm using X here, but actually the oscillation on Y direction, I should use Y here, right? Y axis. Otherwise, it's not really anything much meaningful in terms of direction we measuring. We can just say Y there. So which means if I know this FA in terms of mg is equal K times the Y, so I can rearrange this one. Let's say Y is equal extended amount is equal K over G times the mass. So I can simply do a quick experiment. I can change the amount of mass added into the hanger or the spring in this case, and then look at it how much extension happened. So if I put this into y-axis, this into x-axis, then the slope of the graph going to be the k over g. So I can figure out what is the spring constant by making simple graph. That is this the Hooke's law component. Okay. So data set going to be look like that. This going to be y displacement, amount of mass added. Then I can figure out what is the spring constant by using slope of the graph. That is part 1. Okay, so we have to do that first. After we figure out the spring constant, then we'll go back to the simple harmonic motion. We'll let the spring to oscillate. Then we'll take a look how the simple harmonic motion is actually validated by using that. Okay, but before you do anything, you need to find this spring constant. Okay, let's do that part first. But that part we don't need to have the oscillation. We just need object to attach to the spring and then extend and then becomes stable again. Okay. All right, question. Okay, so if you want to stop the oscillation, you can click on this icon, this red dot right here on the very top, nearby the spring, very top right hand side. So then that will bring into the stable point. Okay, after you attach the mass. Now this is the initial stable point. After you mass the attach, it will come back to the new stable point right there. Click on the red dot, that will bring into the there. Okay. So now what I interested is actually measuring how much extension happened due to applied force. That's what we interested. Okay. So which means length of this green arrow. If I know that length of green arrow varies as a function of mass, you can see if you increase the amount of mass. There you can see slowly size of the green arrow increasing. I can vary the mass added from about 50 grams all the way to 300 grams. So we don't need to oscillate this always. It has to be stable. Okay, we're going to attach the mass, let it extend, and then we're going to stabilize purposely. Should not let it to oscillate this part of the experiment. Okay, any given mass, always we have to make it stable. Then we measuring the starting point of the spring to the extended amount. Now this is the end of the spring. Always we are interested in spring extension. Okay, without mass, this is where it's supposed to be. With added mass, this is where it new location. Now we want to find what is the extension. That is actually this red arrow. You can measure it easily by using this meter ruler. This is a 1 meter long meter ruler, like the general meter ruler we use in class setting. And then the smallest least count for this one going to be, this is 10 centimeters, right? So that means each 1 millimeter is the least count. However, we can estimate half the millimeter level. Okay, so that means I can measure actually in this meter ruler all the way down to the half the millimeter level accuracy. Okay, try to measure as accurate as possible. There are going to be a little bit of error. You can try to zoom in maximum level this page, and then try to observe this end of this arrow. Okay, as accurate we do that measurement, K is accurate. As accurate the K, our next study with the simple harmonic motion will be accurate. Okay, that's the plan. Question. Okay, then that's it. Then let's continue. So let's start this mass very low. Always make sure you click the red dot in this case. We're not interested about oscillation at all. What we're interested is about the extended amount of the spring. Now in this case, I'm adding about 50 gram. The location of the spring, I'm keeping like 2 places away from the smallest possible spring. Technically doesn't matter, but if you this slider, you can see click and drag. Depending on where you place that, numbers you observe going to be different. Okay, make sure if your slider is on different location, numbers you measuring going to be very different, because that tells you what's the type of spring, how softer that is, or how harder the spring is. Okay, so now in my case, I'm in about like 2 segments away from the smallest possible value. Make it stop. 50 gram added. So the amount of extended amount is about close to 10 millimeters, about 10 centimeters. About 10 centimeters. Okay. One thing I forgot earlier to actually mention that. So this is slightly different than our real in-class meter ruler, right? Because each of these number is 10 centimeters. And inside in this part is 1 centimeter, right? So that means each of this is smallest one is not 1 millimeter, in this case 1 centimeter. So that is not that does not match exactly with our in-class least count. So the least count I can go here just half the centimeter, not half the millimeter. That's, you have to correct that. Okay, so each of this number is about 10 centimeters. So each of the small line is 1 centimeter. So I can estimate half the centimeter level, not anything beyond that. Okay, which means the anything error can happen in this measurement going to be huge. Half the centimeter means about 5 millimeters. So that's going to be very huge effect. But let's see, hopefully it will be fine. Since it is a simulator, still we're going to get a nice data set. But the least count is actually in this case not good at all. So this is about 10, but try to read it as accurate as possible. I'm going to read into 10. So let's start working on table number 1. So we are investigating now the Hooke's law. Try to understand the spring constant. Okay, mass in kilogram. 50 grams mean divide by 1000, 0.050 kilogram. And force going to be in Newton. Force going to be equal sign mass added multiplied by 9.81, right? mg. That is the applied force to the spring. Since I can go and then here, this least count, we have to go like what we can measure directly here, not meaningful adding any extra. So I can go like 50 grams, which means the second place will assume we can read it. So if we assuming we can read it down to the 1 gram level, then when I reporting it, I have to record here correctly. So which means I can record third decimal place. Okay. Format cells, right click, third decimal place, because third decimal place showing us 1 gram level. Okay. Because in our simulator, let's assume this is like 50. I can read like if I want to 55 also, which means I can read down to the 1 gram level. Okay. Not anything beyond that. If it is in-class experiment, we can read down to the 2 decimal place on the gram level, below the 1 gram level. So that means the accuracy going to be 0.01 gram. We can't read that accuracy here, only up to the first gram level. So it means the 3 decimal places in kilogram. And the force also you have to have about the same. So which means the 3 decimal places. You may need to reformat those 2 columns. Okay. And the extension, we are measuring with our meter ruler in unit meters. We are measuring it centimeter unit. In centimeter, I can go only about like half the centimeter. So that means in centimeter, I can't go anything beyond that, right? So I have to report accordingly how much accuracy I can read. Right now, my reading is 10 centimeters, which means 0.10 in meters. However, I can actually go half the centimeters. This is first centimeter location, this 0. Half the centimeter means next centimeter location, right? So which means the accuracy right here also 3 decimal places. Not anything more than that. But if it is in class setting, we can go more because that last decimal place in meters is 1 millimeter level. But in class setting, I can go another decimal place. So the accuracy is actually bad in this. And that's it. Then you can calculate the spring constant. You know the Hooke's law. Spring constant is Newton per meter. Hooke's law tells you applied force is proportional to the extension amount. That proportionality constant is the K. K is the ratio between the applied force divided by the extension, no compression. Equal sign, applied force divided by the extension, no compression. Now this is about 4.91 because the spring is very lighter, very softer spring. If I have the heavier spring, then this number right here going to be large. Question. All right, then let's take a look what will happen if I have the different mass. So let's increase this into maybe like 100 gram. You can click and drag or use the arrows. Make it stop the oscillation. Then measure the length of the red arrow. That's about like 20 centimeters. 100 gram, 20 centimeters. 0.100, 100 grams divided by 1000, 0.1. And then the force going to be, you can click and drag actually. Let me write it down, that function also here. We are using force that way and the extension and the spring constant, this command. Okay, that's the only 2 command we need actually this table. Any question so far? This also you can click and drag the last one, but this we have to record that is about 0.200, and this one I can click and drag. Now you can see this spring constant is actually remaining constant for that particular spring. That's a spring property, should not change at all. That actually remaining constant, right? Since this is the simulator, our numbers going to be looks very perfect. But if it is in class setting, we will get a little bit of error. We're not going to get this perfect accuracy, okay? And in terms of accuracy, I can go 3 decimal places. But in terms of significant figures, I can have about like 3 significant figures. So we can keep 1 decimal place here, accuracy, but since this is a simulator, we're not going to see any difference at all. Question. Okay, that's about it. It's very simple. Then all you have to do is just increase the mass at a time like about 50 gram and then measure what the extension is. And you can see it should be like very perfect since it is a simulator. Let's make a little bit of error purposely now. This I'm going to measure into 29. Should be 30 technically, it should be linear, right? But I'm going to measure into 29.29. Then that will add a little bit of error. Now I'm 1.15. This you can click and drag. This you can click and drag. Then you can see now I'm creating the error myself actually, okay? Because it should be 30, but I'm creating right here, I'm measuring it a little bit off into 29 centimeters. Because of that, I get a little bit of error. That's better because if we doing taking the many measurement, the whole idea is that because we can have error points. So at the end, we're going to take the average. Okay. Question. And that's all. Then you increase this into next location, 150. Let's do 200. Measure that also. I'm going to measure into maybe 39.5. That's the accuracy. I'm going to keep that little bit of error there. Try to measure it as accurate possible. 0.2, can click and drag the force and the extension I'm going to measure into 39.5, 0.395. Because I can estimate down to 5 half the centimeter level, that is about 5 millimeter level. That's my estimated value. Check how it changes. I have a little bit of error still, that's okay. Totally fine, that's the idea. Question. If you're doing this in class, you will get like maybe 10 to 15% error, depending on the accuracy how you measure. That is small difference can create a large error, but if it is in-person setting, the accuracy of that length measurement is high. We can measure into the half the millimeter level, accuracy is actually better. But here you can see smallest change I do here for the extension gonna give us huge error here, considerably large error. The reason any error I'm doing here with the extension is half the centimeter, 5 millimeters of error. Okay, that's the problem. Then you continue 2 more data points probably. I can do 250 and then 300. Be like 49.5. 0.25, 0.495, and then my spring constant. And let's do 300. Make sure spring is not oscillating before you take the measurement. Make sure you click that red dot right here. Okay, if it becomes highlighted, the spring will slowly oscillate. Then this size of the arrow is actually not accurate. About 59.5, 0.3, 0.595. Okay, question. That error going to be a little bit higher if you actually measure this way. Now, this arrow, that's you can't see if it is an in-class experiment, right? You can see actually where's the starting point. You can actually point it out where's the starting point of the spring, but you can't really see this arrow, right? So I have to measure length from the starting point right here, this line, to the mid of this oscillating, this mass attached. So I have to assume like the either to the mid of the mass attached or to the end point of the spring, always going to be to the same point all the time. Okay? So if I'm measuring to the end point right here, you can see, depending on how you measure, there are going to be error attached there too, right? So as a result of that, there are going to be so much error can happen even this is a very simple experiment. So if it is in-person setting, those are the important point. We always try to understand how the error going to show up, what type of errors are happening, and then how that error is actually changes the outcome of the experiment. Because then that one important part of all physics experiment going to be part of any of the experiment in future you will be doing. That's the disadvantage because that error going to be very minimized because we have additional uh, advantage when we doing the experiment with the simulators. So that's okay, I think. Question. All right, then let's investigate this Hooke's law. Now, in terms of Hooke's law, force is equal k times the extension, right? So I have the force right here and extension right here. Let's make a graph, force versus extension. Okay? We can do differently actually. We can make force versus extension or mass versus extension, doesn't matter how you did that. Depending on how you did it, then you can get a different answer. Okay, this G, I can put it into here, for example. Then we can consider this whole thing is the force of gravity. Force of gravity is our X. So you can plot the graph any way you like, doesn't matter. If I put here mg together, force of gravity, then the slope of the graph going to be directly equal to the spring constant. That is easier if we do that way. But if I doing that force applied force, the extension versus mass applied, not the force of gravity, then I have to bring the g again and then multiply the slope to figure out the spring constant. Okay? Either way is fine, doesn't matter. But since we calculate the force, we can actually make a graph between these two. That makes it easier, I think. Insert, you know how to make the graph and everything by now, I guess. Should be very easy. We're doing this now many times. Let's add the data. Double click, select the data. Let's add the data now. X-axis should be force of gravity. So which means the C8 to C13. And y values should be extended amount D8 to D13. Click OK, click OK again. That's a nice graph. Linear. So if I have the graph, then we wanted the trend line. Double click. Chart elements. Axis title, horizontal and vertical. And the trend line, linear. Then you know all these things by now, right? If you have a graph, make sure you name the graph. This is extension versus force of gravity, force applied, you can say, for spring one. For spring one, because later we're going to study another spring. Okay, you have to name it properly. This is going to be the force of gravity, which is m times e, unit Newton. And the y-axis gonna be extension y. That's going to be unit of meters. Usually we use this brackets to mention the units. Okay, now if we have the graph, then we would like to see the equation. Double click on the trend line, click all these three icons, then it will show you an equation. So that's what we're looking into. Question.
See, I think you've changed the size of the box once you set up the graph and the normals. Like a rectangle, and I see you change the size.
No, I did not change the size or anything.
Well, when you first clicked on it, it's like a bigger rectangle, but then to a square.
Doesn't matter. You can leave it as it is.
Or whatever way is fine.
Yeah. Let me check that number. Slope of the graph should be the spring constant, right? You can see that's not the number we can have here. So I think maybe I flip the axis. That we have to take a look quickly. Series, edit, x values, force of gravity mg, y values, extension, but why I don't have the slope of the graph correctly? That will be a problem. Let's see why it is.
You have the axis flipped for the graph.
Yeah, that's what. Yeah. So our calculation is fine, I think. Calculation is fine, but the axis flip right here. You have to take a look at that, okay? So let me change that. So when I did the calculation, that's why I checked. So the calculation find C8 over D8. C8 is the force divided by the extension, that is the spring constant. That fine, which means all of these are good. So when I do here, then in our graph right here, x-axis should be force of gravity and then y-axis should be the extension. No, yeah, that's what I did here. This is the mistake which I did. So which we studying actually this part. So the force of gravity should be on y-axis and the extension should be on x-axis. Then it is easier. Let me write it down. That was the mistake. So you can just put this into the y-axis. This is the slope of the graph A. This is going to be just x-axis. That's all. Then the slope of the graph going to be actually, it doesn't matter. You can invert, but let me change that. That is here, I think. Edit x values, force of the x values is the extension and y values is force of gravity. Then it should be fine. I have to redo the equation. Then let's take a look. Now we have to maybe redo trend line. So let's take a look. Okay, so let me do one quick thing. It doesn't show up in my case, but if you have the axis correctly, you are fine. Okay, so x-axis should be extension, y-axis should be your force of gravity. Extension and y, then it should be meters, and then y should be the force of gravity. Force unit should be Newton. And my trend line doesn't show me a equation correctly. Let me get rid of that. Let us do it again. think it will be fine. Should be fine in generally, but I don't know why it's not doing. Still, it's not visible. I did something wrong in the data. Okay, now it's good. All right, if you edit it, make sure you delete everything when you edit the data, and otherwise it's not going to read it correctly. Otherwise it should be fine. So that's simple. Then you name this. What is this? Figure 1. You can name it force of gravity versus extension. So otherwise maybe force applied versus extension of spring number 1. That's it. Question. And also you may need the picture, right? A screenshot of this one. That is for your procedure section. So I will gonna leave it here. You need only one picture for the procedure section since we're using the same simulator again and again. So you don't need to add like many pictures. Just take one screenshot added into here. Okay. That should go into the procedure section. So since that should be figure number 1, then I can start naming this one from figure 2. Okay. So those things, you know, all those things, I don't think we need to go on and on again and again, all of those ideas, but make sure you follow all of those things. Any question? All right, that's it then. We'll continue into the simple harmonic oscillation then. Before we do that, let's take a look the spring constant, right? So from the slope, I'm getting about 4.962. Let's take a look the average here. Okay, so the table number 2, calculated average equal AV, average calculated on column E equal average from column E 8 to E13, about 4.96. I'm getting from the graph about 4.962. That's a good number, 4.962. You can see if it is cut down automatically, third decimal place, I would suggest you to reformat this whole thing, this table, all of these cells into maybe like 3 decimal places. Then you can see a little bit of different numbers in third decimal place. Okay, accuracy is very high. So let's compare these two. The spring constant unit is what? Newton per meters, right? And PD, there's no unit, but we generally use in the percentage sign there. You know how to do that. ABS parentheses. Different between these two, since I'm doing PD, doesn't matter which comes first. And C20 plus C21 average divided by 2 multiplied by 100. Very accurate. Write it down, these two functions. This is going to be kcal avg, and k from the graph going to be just equal slope of the graph. Okay. D going to be this command. All of those you have to add into your appendix section. Okay, question. Right, so that's it. Then let's take a look at the simple harmonic oscillation now. In terms of simple harmonic oscillation, we can actually validate that formula a different way, right? But one of the easiest way to do that actually in the simple harmonic oscillation, I can try to calculate the spring constant by using the period of oscillation. That's the easiest way to do it. Now, if I want to do that, if you look at it, this equation right here, this equation is equal 1 over period of the oscillation is equal 1 over 2 pi k over m square root. Square both side of the equation, then you will get then you will get 1 over t to the power 2, 1 over 4 pi to the power 2 k over m. Now, I can do a couple of different ways this experiment. I can change the mass on the hanger like I done earlier from 50 gram, 100, 150 and then so on. I can find period of oscillation for each mass. So which means you can still do the graphical method by varying the mass and then accordingly the mass, the period will be differ, right? So which means this will be our x coordinate, t going to be our y coordinate. I can rearrange this one little bit, t to the power 2, which is equal 4 pi square divided by k times the mass of the mass in the hanger. Now, which means if you look at it, this one, if I put this part, let me take a look. My Excel is always doing this crazy thing. Let me check why. One over t square, 1 over 4 pi square, k over m. Then let's rearrange this one little bit. T square equal 4 pi square over k times the mass. Now, if I put this into y-axis, this into x-axis, this is going to be slope of the graph, this part. So which means I can make a graph if I have the variable mass putting into a x, t to the power 2 putting into the y, and then you will get another graph look like that. Same graph like that earlier. If I do the trend line, slope of the graph is equal 4 pi square over k. 4 pi square is a constant, slope is known, I can calculate k again. So which means I can validate that whole concept behind the simple harmonic motion by just measuring the period of the oscillation with the different masses and then re-estimating the k, then we'll compare that k coming from the simple harmonic motion into the previously you calculated from the Hooke's law. If those two match, then you can validate the theory. Okay? That's the plan for the next part. To do that, I have to let this to oscillate and then find the period of oscillation. That's all we have to do. Very simple idea. Okay, table number 3. So we can, where is the mass like we done earlier, starting from 50 gram and then measure period for 5 oscillation and then divide by 5. We'll get the period of oscillation and then take this form and then we'll calculate the key. That's all. Question. Mass is in unit of kilogram. Period always unit of second. And t square going to be unit of second to the power 2. And then spring constant going to be force over extension, Newton per meter. Now to do that, now that part is the critical, right? Because if anything wrong in the period of the oscillation, our calculation going to be very inaccurate, right? So let's go back to the smallest mass attached. Let's get rid of this extra velocity component. All of these, we are not interested in any of these, right? So what we interested is now period tracer. That's what we interested. So let us stop this one first. Now we have 50 gram attached. We are not measuring any length or anything now. So you have to give the oscillation. So don't give like very large oscillation like that. Instead give a small oscillation. Like maybe if it is in-person setting, like we're going to give usually about 2 centimeter oscillation. Very small oscillation like that one. Then this will go up, come down, and then do that oscillation forever because energy is conserved. Now, since we're doing this actually in slow-mo mode, I can, if I want to find the time for one oscillation, but let's do for 5, okay? All you have to do is start the watch, make sure clock is on 00, and then start it running at selected point, okay? And then count 5 cycles. Stop the clock, take the timer, that goes to the table number 3. And then you count 5 of those black lines, okay? Black traces, that's a period tracer. That's the second one for me. Third one. Fourth one. Fifth one. So our reaction time will give us error a little bit because how you started that when the black tracer appear and when you stop when the black tracer completing, there will be a little bit of reaction error there. That's okay. So that will be our percentage error at the end. So in this case, I'm getting about 4.39 total. I may have to quickly reopen this Excel sheet. It actually not responding at all. Okay, give me 1 second. Usually, if I have many application open, sometime it happens. Okay. Fine. Okay. Any questions so far? Mass is 50 gram, 0.05. Time for 5 oscillation, we got 4.39. And the period of oscillation means time for 5 divided by 5, about 0.88. Since we are on slow-mo mode, we can even get that directly. T square equal t to the power 2. And then let's calculate the spring constant by using our equation, which we built earlier here. So we're referring actually this equation. So the period of oscillation T is equal to pi m over k square root. We square it earlier, 4 pi square m over k. So if I want to calculate actually k from here, k gonna be equal 4 pi square times mass divided by t to the power 2. So let's check it out, that one first. Equal sign 4 times pi to the power 2 pi squared multiplied by mass of the hanger divided by t to the power 2. Still I have a little bit of error. Let's see why I have a little bit of error there, where it's coming from. Oscillation, I think period of the oscillation. Let's see why is that. Check it out that again for one period of oscillation. About 0.61 second. That may be the problem. Let's check it out, that one. Now you should be able to do this calculation. It's not a big deal. Okay, so let's see this one. 5.61, yeah. So which means earlier my measured value is actually not very accurate. So I'm getting about like 20% error or 30% error. That's not really good. So I may need to take a look the time for one period of oscillation. So I did some mistake earlier, I think, when I counting 5 oscillation. Okay, I may count more than 5. I think it should not be 4.39. So if I do one oscillation now, just directly in the slow-mo mode, it's about 0.61. Earlier I got about like 0.88. So the error is too high, 30%. You may have to check that carefully. Okay. So whatever the error happening there are going to be huge, because the reason in your equation, this is t to the power 2. Okay. That's t to the power 2. There's no other error come from there. If you have that correctly, k going to be very accurate. We expecting to be, the spring constant is about like the same number earlier, 4.9, about like 5.0. Now we are good, but my period of oscillation should be 0.61. So I did maybe something wrong. If I have that number with 88, I may not getting that one. You can see the error is much larger, about 30%. I have to recheck quickly the time for pi oscillation. Okay. Yeah, if the period tracer is skipping, maybe that's not good idea at all. Yeah, I think so, because it actually is skipping. So if you want to use the period tracer, that's a very good, very good point. I remember that happened last time too. If I want to use the period tracer, I can't count number of period tracer. You can see it actually wait until this object come back to this point, right? See that it disappear, wait it, appear again. So there's a skipping time. So I should not use that one instead. You don't need that. Just calculate the time for pi oscillation yourself. Let it start when the object reach this black line right here. Let's count pi oscillation. Okay, that may be the best way to do.
Sorry, we can measure the time for one oscillation and multiply that by 5.
No, that is not the idea here. That's not meaningful. Idea here is actually if you go in this normal mode, this oscillating much faster. You see that? So you can't really, because we try to simulate the in-class experiment. That's how the in-class experiment look like. You can't really find one oscillation time. It's going to be very fast. So you count the time for 5 oscillation, divide by 5. So the opposite direction, not meaningful at all. Now let it oscillate this way and then count the 5 oscillation, which means if you are starting from the very bottom point, it should go up, come back to the bottom point, then 1, okay? Then go up, come back to the bottom point 2, and then so on. Go in slow-mo mode, that is easier, but count for 5 oscillation. Go up, come back to the bottom 1, then you wait until it go up, come back to the bottom point 2, go up, come back 3, go up, come back 4, then go up, come back 5. So now you can see earlier time is actually incorrect. So that's the problem. 3.62, then we should be fine. Still little bit larger. So that means still I'm counting little bit higher. So, but that's okay. That's why we're going to take a couple of different data points and then see how it varies. Okay. Yeah, 3.11 should be fine. I think that's better value. Yeah, anything more than 3.5 going to be much higher. Because if you have this number higher than 0.61 period of one oscillation, then you will get huge error there. Okay, there's two ways of doing this. Since it is a simulator, we can actually find time for one oscillation, but we would like to do 5 oscillation to simulate the in-class experiment. Okay, that's what we're trying to do. Okay, just take a look at that number. Okay, this should be about 5.0. Then we find. Then increase the mass. count the oscillation again, 5 oscillation, and then we continue. So I'm going to try this one more time without the period tracer. Maybe you can use that green arrow, then you can see actually one particular place to start and then one particular place to stop. Okay, that might be a useful. I'm going to start when it reach actually this blue line on the top. One, two, 5. Yeah, it should be around 3.1, 3.2. Then I think you're going to get a right number. Good. So I have a little bit of error there. Just leave it because that error going to be very high if you're doing this lab in-person setting, because it's very difficult to get that timer in-person setting. This is what you're going to observe. That's what you're observing. Okay, then you can think about how harder to do that. It's going to be go up and down really faster. Okay, so we're going to get like little bit of error. That's okay. All right, let's continue. Stop this and then increase mass into about like 100 grams. Oh, let me copy paste that equation right here. What we're doing in terms of equation, you may need this formula, right? That's the equation for T, then T square e to the power 2, and then this equation for the spring constant 4 pi square m over T to the power 2. Okay, then it's the same thing. You have to just repeat it for different mass values, right? Like we done earlier. Question. Okay, let's do that maybe 100. And also in terms of sig fix, you have to recorrect again here, right? You can see mass is, I'm observing only 2. I have to have 3. In terms of time, you can go 2 decimal places after second. That is fine. But this column, make sure 3 decimal places are visible, because I can measure up to that point in terms of kilogram. Time is fine up to 2. That keep it like that. And then spring constant fine up to 2 decimal places. Okay. Question.
Sir, I get more than 4 for the time for 5 oscillations.
No, that too much. That too much. Definitely your error gonna be very high there. You have to have a number around 3.1, 3.2, maybe like 2.95. That will be a good number. Anything more than that?
What am I
Oh,
doing wrong?
and also you have to check where's your spring constant this slider is. In my case, it is 2 segments from your smallest point, okay, to the right side.
Mine's 2 segments away too.
Then you should get about the same. Then you're counting wrong. That's the only thing you're doing wrong. When you count in the 5 oscillations, you're counting it wrong.
Okay,
You need to
let me
take a
try
look
again.
that. Yeah, you have to take a look that again, okay? Any other question?
Sure, when I do 5 complete oscillation, it always comes down to like longer than 4 seconds.
Still, 4 seconds is too high. You're gonna get a lot of error actually. 4 seconds is definitely too high. It could be around 3 seconds, 2.9 seconds, maybe fine, but anything more than that, your error right here for the spring constant you calculating, we expecting that to be about like 5, right? Even for my case, 3.0, you can see it 5.4. Still, I have considerable error there. To get it into like around 4.9, 5.0 level, my timer there should be actually a little bit different. Calculate with that number. That's okay. Just use that value, 4 seconds, calculate the spring constant, take a look how much the error is. If it is reasonable, just leave it. Don't need to worry about too much. Don't need to worry
Okay.
about like try to get like exact number because reverse engineering the calculation, right? So it's not what we do in person setting. So don't worry about too much. If it is like around 5 less than 10% error, I would suggest just leave it. All right, then let's continue. All we have to do, increase the 100 gram, give a little bit of like maybe 2 centimeter oscillation, and then the mass is larger. You can say it's easy to measure now oscillation, right? So you get a better number as the mass becomes higher. So that's all. Then you let it oscillate, count time for 5 oscillation. You can use this movable line if you want to identify one particular location. I'm going to use it to the very bottom point. I'm going to start the timer when it reaches there. Try with that number and then see what we get. 4.33. Take 7. About the same. I'm expecting 5.0. I'm getting 5.2. So whatever the error in my time measurement is actually consistent. Okay. So likewise, you continue. So increase the mass to next number and then so on. That's all really. It's nothing new to do. Increase the mass at a time about like 50 gram and then repeat the measurement. Okay. Calculate each point the K value, the spring constant, and then take a look how much the difference is. If it is about like 0.1, 0.2 difference, I would suggest don't need to repeat it. But if it is a large difference, repeat it. Okay. Stop at this point and then let's give a little bit of extension all the way up to maybe this level, like maybe 2 centimeters. Okay. Make the stopwatch 0. So there are going to be a human error now, right? Because I have to click when that is starting that point up, and then I have to click again when it reach back after 5 oscillation. So there's 2 human errors. The reaction errors is actually happening there. Okay. So now 0.150, and the time for 5 oscillation I'm getting 5.35. Let's take a look how the calculation. About 5.17. You can see when the mass is heavier, then it actually takes more time to do one oscillation. As a result, my error getting actually lesser and lesser. So that's better. You can see this number getting closer to now 5.6. So that's one good thing. Let's do next mass, 200 gram. Let's stop here, do about like maybe two, say I'm using this extra red line. If you click this movable line that will appear there, you can click and that wherever you want to start. I'm dragging, click and drag up to that point, let it oscillate. We are measuring 5 oscillation, okay. .23, let's check with that. 0.2, 0.23. Then let's click and drag all of these. Better. You can see now error is actually getting lesser and lesser. I'm going to the point where I needed, because number we needed 4.96, very close to 5.0, right? Now we get in there, because now means now the oscillating is actually much slower. So I can identify each oscillation carefully, right? So that's the idea. If you go back to the 50 gram oscillating much higher, then I can't really see my reaction error going to be too high there. Okay. That's all really. So just leave that first 2 point going to be a little bit of error. .94. This is 250.25. And around the same 5.12. Let's do one more data point. Any question? .64. Now we are on 300 grams, 7.64, 5.07. So first data point is the highest error, but everything else after that I think looks fine. You can repeat first data point if you have a really huge error, but I'm gonna leave it like that. Okay, any question? We will check the error on table number 4. Right now, I'm not calculating the error. I'm just checking this number with the expected value, right? We're expecting about 5.0, but I just directly observing how much the difference is. Closer to 5.0, error is lesser. Away from 5.0, I have a huge error. Okay? So let's make a graph. Now, earlier we mentioned that we can do this check by using the graph, right? Because mass is a variable, t is a variable. I can make a graph. Let's do a graph t square versus m, right? So this is going to be the mass on x-axis, t square going to be on y-axis. Slope of the graph going to be equal 4 pi square over k, which means the k I can calculate. K is equal 4 pi square divided by slope of the graph. That's the plan. Okay, so that's very simple, like we done earlier. So let's make that graph. It's scatter plot again, and then all of these. If you have any difficulty, always ask. But I basically assuming that you guys are fine with graphing and everything. That's why I just proceeding without explaining some of this step. But always, if you want to repeat, just ask. Okay. Insert the scatter plot, select data, and now x value should be mass, that is B29 to B34. Y value should be t to the power 2. Okay. So that is E29 to E34. Click OK. Click OK again. Then let's add axis title and the trend line. Then let's check the slope of the trend line. So slope of the trend line is 7.7255. By using that, I should be able to get the K by using the slope. Okay, let's check that value. Equal sign, slope of the graph. We know the formula earlier, we discussed that. Formula gonna be K is equal 4 pi square divided by slope of the graph. Okay, equal sign 4 times pi square 3.14 to the power 2 divide by slope of the graph 7.7255. 7.7255. 5.10. That's very close to 4.9, 5.0 value. So we are good. So the data looks fine. So I think let's take a quick break here and then we'll come back and then continue. Okay. If you have any question, any point making graph or anything, is still ask. Okay. Even this is the last lab. I know you should be fine by now, but don't worry about asking anything. So investigate spring constant by using the simple harmonic motion. Okay, if I'm getting the same spring constant, which means everything we build, concept and theories for simple harmonic motion is correct. Okay, so that's the idea. So we can validate all of them by just simply comparing these two numbers. Now, again, these things now you know, if you have a graph, you have to name it properly. This is going to be now time to the power square. And say actually period square versus mass for spring 1, because we're going to do this for another spring. Okay, spring 1, x-axis is going to be the mass, units kilogram, y-axis is going to be the time square value or period square value. Units should be second to the power 2. And then we have the slope, and then make sure if I have the graph, I have to name it right. So I name previous one figure 2. The reason there should be one more figure on your procedure section, at least one. If you have more, make sure you follow all of those things. It's going to be now period square versus mass for spring 1. Okay, any question? Okay, let's analyze the spring constant. We know unit should be Newton per meters. Since we done earlier spring constant calculation for the table 3 few more times, let's do the average. Equal average of F29 to F34, 5.18. That's going to be the cal average. So this is going to be the K calculated average, and then K from the graph. K from the graph is actually 4 pi square divided by slope of the graph. Okay, that's two equation we needed there, and then we need percentage difference between those two. So let's compare that. Equal sign, ABS, parentheses, difference between these two, doesn't matter what comes first because it percentage different, divide by the average, addition of C42 plus C43, divide by 2, multiply by 100. About like 1.5% difference between them. That's a very good sign. Now it asking another PD here, two of them. So what it asking is actually compare the calculated average to the previous calculated average here on table number 2, and the graph value from graph number 2 to the graph value from graph number 1, that is this number. Okay, about the same numbers, but let's do that calculation. This is actually for PD of case from is simple harmonic motion. So that's what actually we do in there. And then we'll do 2 more PD values. So this one it asking you to compare ABS parentheses this number minus number on the table number 2 calculated average C20 divide by parentheses addition of those two C42 plus C20 divide by 2 multiply by 100. About 4% error between them. Calculated average to calculated average. Okay. So this is PD. But that PD we do in this K cal average. Between K cal averages between this one and the previous one. Okay. And this one is actually comparing K from this graph to the previous graph because we calculated the same K by 2 different graphs. Equal sign ABS parentheses C43 minus C21 divide by parentheses C43 plus C21 divide by 2 multiply by 100. That value is actually better. Percentage error is lower. So this is actually PD between graphs. Okay. All right. Question. PD, there's no units, but usually we leave this percentage sign there. You can leave that one as it is. All right. Any question? Okay, now next part, the whole next tables. Okay, there's another 4 tables. Now it's the same thing. Okay, it's nothing new there. What we're going to try to understand how the spring, because we know a spring constant should be depending on the type of the spring. So we will change the spring and then reinvestigate this one. Okay, since you know everything how to do, that should not be difficult at all. So let's continue. So all I have to do is actually select a new spring. So if I want to select the new spring, then right here, you can actually do that by doing a spring constant into a different value. So if it is incursion setting, we're going to get rid of this spring, attach the new spring. Now I'm going to click this and then drag into the other side, larger side. Then you can see thickness of the spring changes. And you can see now everything will change accordingly. Okay. Let's bring the mass back into the 50. Get rid of the mass here first, that is the spring relax position. If I attach the 50 grams, make it stable, that's the amount of extension. If I measure that length, that's about just maybe 5 centimeters, not more than that. It's been half of the previous, right? So you can see depending on how stiff or how smooth the friction is, depending on that, K value will be very different. Now this is going to be then stiffer or the heavier, stronger spring. So I need a lot of force to actually give extension. Earlier, if you remember table number 1, within 50 gram, it extend about like 10 centimeters. Now the extension is actually half of that. So the spring constant will change accordingly. Okay, let's check it out this one then. Mass attached, kilogram, force going to be mass times mg Newton. Scale, we're going to measure unit meters. Spring constant, same, Newton per meter. Let's continue. Now you know what to do exactly. Mass, we're going to start with 0.5, but remember we can actually go 3 decimal place, all of these. So I'm going to reformat that one. Force going to be equal mass times 9.81. And then extension now about just 5 centimeters, which means 0.05 in meters. Okay. The spring constant going to be force applied divided by the extension. So it is 9.81 now. Earlier it was 4.9. Now it almost twice now. Okay, not exactly twice, but it almost twice now. So spring is actually stronger, more stronger than the previous. That's what this spring constant tells you. And then you just need to repeat this, right, again and again. So it's the same command. There's no any difference at all. So this will be the force and this will be the spring constant. Okay. Do this with the 100 grams. Make it stop before you take the measurement for this case. Okay, 100 gram about 10 centimeters, 0.1, about 10 centimeters. So this you can click and drag. This also you can click and drag. About 9.81, same. This part is easy actually. The measurement and the error is actually very less. The oscillation part is actually the trouble, right? That can give you a lot of error. Let increase the mass 150. Stop me and ask any question. Since it is the same thing, I'm just repeating to make sure we actually complete everything in the class. Otherwise, you should be able to do this without any problem. So it's going to be about 14.5. I'm going to read it into the little bit of error there. 0.15. This I'm going to read 145, 14.5. About 10.15, little bit of error there. That's okay. 200 grams. Stop the oscillation, then take the measurement. I'm going to read into that also 19.5. You can read into 20. It's very close. 20 should be the exact number, I think. 0.2. So you can click and drag. Yeah, so 20 is the exact number, but if you read into 0.5 or less, then the error going to be so high. The reason is actually the least count of this meter ruler is about 5 millimeters. Okay, that's why. And let's do 2 more data point, 250. I'm going to read that into 24.5. Okay, 0.25.245. And then next one, 300. Read that also into 29.5. Okay, question. All right, then let's do a graph because I have a data set. I'm gonna actually copy paste this graph. Okay, so you can make a graph from the beginning from scratch, but since it is the same graph, I'm gonna just copy paste that graph into here and then edit the data. Okay, that makes it easier. So double click on the graph, select data, and then let's edit the data. Series 1, get rid of anything on X. Okay, because X value shows you the graph number 1 X value. Okay, extension values, but I need now table number 5 X values, okay, extension values. That means D52 to D57. Then Y values, table number 5, force of gravity, C52 to C57. Click OK, click OK again. Graph name also you can copy paste. And it makes a little bit easier to do that. This is figure now 234. And all we have to do edit this part right here. This is now for spring 2. Everything else actually the same. So I don't need to spend a lot of time to doing the same thing again and again. That's the idea of this whole semester. So the idea of that we skip using the calculator. If you're doing this kind of calculation by using the calculator again, you can see how much time you're wasting, because same type of calculation, every table, you have to repeat it 6 times by putting the numbers. But if you do the Excel, then you can minimize that time. You just need to do one calculation per table and everything else automatic. Same for the graph. If I remake in the same type of graph, I don't need to redo the graph. I can just need to edit the data. So the slope is 9.96. That should be close enough. Expected value going to be around the same. Question. Okay, then let's continue. Table number 6. Spring constant for the spring number 2. Newton per meters. Calculated average. Same thing. Average. E52 to E57. That's the cal average. And then from the graph, that is just slope of the graph, right? That's the number in front of x, 9.9623. 9.9623. If it doesn't show all the data point, you can actually reformat this into show at least maybe 3 decimal places. Then you will see that numbers are slightly different, not much. Okay? So the K from the graph going to be simply slope of the graph. To the PD question. Same thing, okay, PD, ABS, parentheses, different between these two. Doesn't matter which goes first because we're doing PD, not PE, right? Divide by double brackets, C64 plus C65, divide by 2, close bracket, multiplied by 100. Well, it's very, two numbers are very accurate. Percentage error is less than 0.5, so that really extremely accurate.
See, it changed it,
Say it again.
the sig figs, like you rounded it an extra place for the percent.
Yeah, you can add the extra decimal place.
Maybe you didn't do it for spring 1, I guess.
Spring 1 also we did.
Oh.
Yeah. Okay, any other question? All right, then it's the same thing like we done earlier. Now we validate the simple harmonic motion. We actually know everything is nicely matching up. Let's check the oscillation for this spring. This spring oscillation going to be too faster because it's more stiffer. Because of that, it's going to oscillate actually really faster. Maybe we're going to get higher error there. Okay, that will be the problem, but that's okay. Let's try. So heavier the mass, it's going to be easy to do. You observe the oscillation, but when the mass is lower, you can see that how faster that moving up and down So that's going to be a little bit tough to do the measurement, okay? But let's try. So let's see. Let's do slow-mo mode. That's the best way to do. And also let's do a smaller oscillation. Like that much. Okay. Make sure the damping is 0, okay? Due to any reason, if the damping is there, then everything is incorrect. So don't change the spring constant, that place where we have. That should be same as the previous case for this one. Then you measure a time for 5 oscillations, same way you done earlier. Okay. 2.19. Now you can see it's moving faster, right? So because oscillation time is less than the previous. Angular mass in kilogram, time for 5 oscillation unit second, period of oscillation going to be unit second, t square going to be unit second to the power 2, and spring constant from the simple harmonic motion going to be again same unit, Newton per meters. So mass now about 0.05. That's the difficult part right now. You can think about now if you're doing this in class setting, if this is the spring, this is not what you're going to observe. This is what you're going to observe. I'm getting the period for 5 oscillation. Even for 5 oscillation period is just 2 seconds. Very difficult to do. Okay, so the error going to be too high. You can have even like 20-30% error because that time is not correct. So let's see what we get. Again, the mass, I'm going to leave it 3 decimal places, right? We can measure up to that. But the period of oscillation, fine, 2.19. Divide this by 5. One oscillation is about 0.44. Let's take the square of that to the power 2. Then let's calculate the spring constant. The spring constant we figured out earlier. 4 pi square m over t to the power 2 equals sine 4 pi to the power 2 times mass attached divided by t to the power 2, which is E73. About 10.28. My expected value should be about like 9.9. We are fine. So that when the mass is smaller, it's very difficult to do the oscillation measurements. So that totally fine. If you're doing this in class, you're not going to get that much closer. You're going to get huge error actually there. Heavier the mass, spring is starting to oscillate slower, then we can actually measure that more accuracy, okay? More accurately. Question? All right, then all you have to do, it's the same thing, right? All we have to do, increase the mass to about like 100 gram. And then we have to do again the oscillating. I'm going to oscillate about like little more than the 1 centimeter here. And let's measure 5 oscillation. Now you don't even don't need the slow-mo mode. You can see measurable now, right? You can do even you can do slow-mo mode if you want to, but I'm going to just do the normal mode to see whether I can get the fairly accurate value, okay? 3.10, let's see. Whether I can get good accurate value that way or not. Not bad actually. I'm not using actually slow-mo mode at all, okay? I measure normal mode. So the accuracy is about the same as previous number. So I'm going to measure continuously with the normal mode. But you can measure in slow-mo mode because it's available in our simulator. Let's do 150. Any question? I'm keeping this like this red arrow, red line right here to measure the lowest possible place it coming up, coming down. Then I'm referring that as my reference line. Then it go up, come back to the same line, one oscillation. Go up, come back to the same line, two oscillation, and then so on. That's why I'm keeping this. Okay. If you click this movable line right here, right hand side, very top, it will appear. You can click and drag anywhere you like. Anything like 2 centimeters from the stable point black line. It's 0.81. Let's check it out, that one. Too high compared to the previous two numbers. Maybe I did a mistake with that number of, yeah. So I have to recheck that number. 150, I need 5 oscillation. Let's check it out, that one. .78. Okay, so that 3.78. Okay, yeah, good. So I can do that oscillation actually counting without slow-mo mode. Okay, error is a little bit high, but that's okay. I'm gonna leave it. Let's do 200. Any question? For 0.35, 0.2. Not bad. Error is about the same. Next mass value 250. .86 for 5 oscillation. 0.25 of gram, 4.86 for 5 oscillation. About the same. 300. .39. Okay, guys, question about the same. Okay, then let's validate, right? So now this part is very simple. We can repeat like this many different spring. There's not much meaningful. So let's validate this one again. That graph also, since we made the graph earlier, I'm just gonna copy paste that graph right here, graph number 2 to here, and then edit the data. Okay. Name of the graph also I can copy paste. And this is gonna be now gonna be figure 5. It's gonna be string number 2. Right? Yep. All I have to do, edit the data, double click, select data, series, edit, delete anything on the X position previously because it is still reading the table 2 values, right? Go to table 6 now, table 7. X value is going to be the mass, right? That's going to be B73 to B78. Y value should be now t to the power 2 on table 7, E73 to E78. Click OK, click OK again. So it will do the calculation automatically. I did a mistake because the number right here not reading correctly. Let me take a look at that again. Oh, that should be fine because slope is not directly the spring constant, so I have to check the calculation. That's fine, just leave the number there. Question. And also you have to edit this term right here. That should be spring 2, right? So that's easy. So we don't need to repeat that all the steps we done earlier. Okay. That's the way you can minimize amount of time you spending for the lab work. Question. Right, then let's do the same analysis, spring constant analysis, Newton per meter. We have the calculated values on table 7. Let's do average. Before that, I will copy paste these few commands. Period of oscillation we done here. And then t to the power 2, that command you need. It's the same kind of command, okay? There's no any new command, and the k gonna be this way. Okay, that's three command we used on that table. In table number 8, let's do average of k calculated, average of cell F73 to 78. So that's gonna be k cal average. Okay. And let's do the k from the graph. Then that's gonna be 4 pi square divided by slope of the graph, right? So equal sign 4 times pi square divided by slope of the graph 3.824. 3.824. It's about the same. Copy that function here. That should be k from graph. Okay, any question? All right, then you compare this you done on the previous table. It's the same thing, okay? Please ask any question, okay? If you have any difficulty on any, since we repeat in the same calculation for second time, I just went a little bit faster there. But if you have any difficulties, always ask, okay? Compare these two first. For the second case, ABS parentheses, calculated average minus the graphical value divide by average between those two, C86 plus C87 divide by 2 multiplied by 100. That two values are extremely close by. It's going to be PD for this case, okay, comparing K values. And then let's compare these values with the previous graph, right? Case 2, spring number 2, but for the previous graph, okay? So previous table. So the previous table, I have calculated average, ABS parentheses, calculated average for table 7 versus calculated average for table 6. Okay, right here. Divide by parentheses, addition of calculated average from table 8 plus table 9 divided by 2 multiplied by 100. About 3%, about 4% average. Okay, so this is going to be PD calculated AVGs. Question. And on the last calculation, let's compare the graphical values from this graph to the previous graph. Okay, equal ABS parentheses, graph value from this one to the previous one. Close brackets, divide by double parentheses, C87 plus C65, divide by 2, multiply by 100. About the same percentage error for both cases. Numbers are fairly consistently close by PDs for graphs values. Okay, question. Yeah, there should be one screenshot for the operator section. I think I mentioned earlier right here, figure 1 should be that one, right? You can say simulator for Hooke's law, and simple harmonic motion. Okay, for that, I think I took the picture earlier. Let me take a look. Yeah, you just need one picture. It's the same simulator. There's no meaning taking many pictures. So just that should go into the procedure section. Okay. All right. Any question? Okay. Then I think we can finish the lab from here. So that I think should be fine. So then let's go back to the previous chapter and then we'll start. We'll take a look at least one or two questions there. Okay. Anybody have any question, concern? All right, let me open something to write up.